Hi, this is Thursday, November the 7th, and what I'd like to do today is walk through Chapter 9, related to, in some distance, to Chapter 7, and then Chapter 8. Chapter 8 and Chapter 9 are very similar. We'll talk about that and how different they are. This homework is due on Tuesday the 12th, and there'll be a exam 3 later next week, but I'll talk about that in a video review around midweek. Okay. We know, if you remember from previous survey videos, Chapter 7 is about confidence interval. Here we don't know what the parameter is. And you remember the path that we have. We can't go from population to parameter. It's prohibitively expensive, both in time, personnel, costs, all of that, financial costs. So we draw down a sample, and our single point of sample, as you'll remember, it's representative. It's got of sufficient size. You remember from Chapter 6 and the formula there. Something greater than 100 or greater. And then that gives us some efficiency in that parameter, or that pathway that I've drawn before, in our estimate of that population parameter. Here we don't know what the parameter is. We're trying to estimate it with our sample. And so what we do is, and the larger the sample size, the more efficient the estimate is. As you can imagine, the most perfect sample then would be whatever the population size is minus 1. If it's 1,000,000, then 999,999. Of course, that'd be very expensive to do. But you know from Chapter 7 or 6, sort of the conceptual and mathematical properties of sampling, where sampling sizes of up to 1,000 are pretty good, reasonable estimates of the population parameter and size of the population. Sampling size is not really so much determined by population size as it is determined by how precise you want to be in estimating that parameter. So anyway, in confidence intervals, what we say is 95 out of 100. You remember there are 3 normal curves. The one that we assume is in the population, because it's over 100, probably 1,000,000 or something, let's say, if it's San Antonio. And then we have our empirical sample, our normal curve from our empirical sample, and it also normalizes because for the most part, we have samples that exceed 100. And then we have one in the center, if you remember that from Chapter 7's video. That intermediary normal curve is it's a hypothetical, kind of an abstract concept, and it's derived by, if we were to draw down 95 out of 100 samples of the same size, then they too would take a normal distribution. 100 samples, or if we drew down 100 samples of the same size, in accordance with that theorem in Chapter 6, they would take a normal distribution. And so what we do then in that middle one, that one becomes then the distribution of those hypothetical 100 samples, 95 out of 100 of which create the boundary, the 95% probability, so that we have 5 out of 100 probability of not trapping that parameter inside the confidence interval. The concept here, and I don't want to go into all that detail because you have a previous video I know, but the concept here is everything inside here is similar. So whatever defines this, like whatever your value is, if this is 20, let's say, in our point estimate, and this is 23, and that's 17, then somewhere between 17 and 23 we believe the true estimate or parameter lies. We think it's our single point estimate, but we know that there'd be some variability in those 100 samples because each sample would be, for say 1,000 people, would be 1,000 unique people in each sample. So we can expect some variability if we're talking about averages or means, or proportions for that matter. Similar. But when we get to Chapter 8, we look at it differently. Here, we know what the parameter is. We know the parameter in Chapter 8. What we're trying to determine is whether our particular sample finding is significantly, statistically speaking, different than the population parameter. Like those illustrations in the front of Chapter 8, there's one there, and we've talked about that in the previous video on Chapter 8, that elder crime in a neighborhood, let's say, we want to do an intervention, crime education among the elderly, and we want to show that the crime rate among the elderly in that neighborhood is higher than the crime rate for the overall city. So we do our analysis with the idea, the null hypothesis would say that whatever you find in your neighborhood as a crime rate for the elderly is not statistically significantly different than the overall. It's just trivially different. The numbers, you can see the difference in numbers, but it's only trivial, not significant, statistically speaking. And so our research hypothesis is to try and reject that if we wanted to demonstrate that in fact they have a higher crime rate. So that would be justification or evidence. If we were into program management, that would be evidence of why we need that program for crime education for the elderly, because they are indeed statistically significantly different in their crime rate than the overall city. And if you remember, there are steps 1, 2, 3, 4, and 5. We'll talk about those again in a minute. And the tails of the distribution, here we didn't want the tails. That's dissimilar. Inside is similar. Here we don't want inside. We want dissimilar. We want to show that our finding in our sample is dissimilar from our parameter. So we want to be able to reject the null of similarity. So we place the null here in the center, and then our values are out here somewhere, and we want to show that distance, even spatial distance between the two, is statistically significantly different, so that we can demonstrate the value of intervening in the elder population and providing that crime education. So we've walked through that in Chapter 8. In Chapter 9, it's pretty much the same thing. I should point out again, because it's the same here, is that you can do this. There are 3 ways that they present it here. Two of them are large sample sizes. One where you're looking for the proportion in a population compared to, or you're looking to show that the proportion in your sample is statistically significantly different than the proportion in the population. And then one where the mean in your sample is significantly different than the mean in the population, one being a categorical variable, the proportion, one being a continuous variable, being the mean. So you want to keep that distinction in mind so you know which formula to get, and this is true for Chapter 9. And then if it's a sample size under 100, then you'll use that t-distribution, if you remember. So there are 3 formula really in Chapter 8, and there are 3 formula in Chapter 9. The principle holds the same. Over here, this is a 1 sample case, this is a 2 sample case, and I'll talk about that in a second. If the sample sizes in Chapter 9 are 100 or over, and it's a mean, you use 1 form. If the sample sizes, or formula, if the sample sizes are larger than 100, and it's a categorical variable or proportion, then you use the other formula. And if the sample size is less than 100, then you use the t formula. So where the sample size is over 100, you use a z distribution, which is in Appendix A, and if it's under 100, you use the t distribution, which is Appendix B in Healey. Okay, now when we're drawing this down, the sample, we have a choice to make. The opening of Chapter 8 talks about, or 9 rather, talks about the differences in attitude on a scale of attitude having to do with gun control, and it's relative to gender. So the sample, in this case, this is a 2 sample case, and this is a 1 sample case, Chapter 8. 2S means 2 sample. So here we're thinking that we want to look at the difference between male and female. Now, we're interested in what it is up here in the population, indeed. This is what we're trying to do. But we're drawing down a sample from the population of males and females. And we can do it a couple of ways. We can draw down a sample of males, and then draw down a sample of females. But most often what we do, rather than do 2 samples, which you can imagine could be expensive, we draw down a single sample and split it out, females and males. Now, let's just say, for example, whereas here, let's say we wanted a sample of 300 and thought that was a sufficient size sample to get the determination that we wanted about the significance between our sample finding and the population parameter. Here we might decide that in order, and this is normally distributed, we want this to be normal, each one of these to be normally distributed. So we might, and if we think 300 is a good one, we might do 300 here, 300 males, and 300 females to make sure that we got an adequate size N in each one. Anything over 100 in each one of these will get us some good readings of the differences between the two. Okay? So in a sense, we're drawing down one sample, but we're being mindful when we do that we have an adequate number of cases, or N, or sample sizes, for each male, for the male side, or male category, and the female category. Something to keep in mind. This is the way it's generally done. You don't usually draw down two samples, but you draw down a single sample with the idea that at some point you're going to split it, and you want to be sure that in that split you've got adequate number of cases in both sides of the split. All right. Now, having said that, let me draw that back here. Let me just use the black. I think it works better. It's a contrast, I think. Here. One of the things that we want to do, we have female and male, is independent sampling. So we want to take care when we sample males and females that they're independent of one another. For example, you can imagine, I can ask you the question, but it'd be hard for you to answer, but you think about it. If we went to the door and knocked on a door and a male came up, we need some males, we need some females, and a male opened the door and we'd ask them the question about gun control and scale them, and then we could say, may we speak to your wife, so we can get female side. What might be a problem with that? Think about that for a second. Okay, a second's gone by. And what might be the problem is they might influence one another. If they live together, they may come to some idea that they're both against gun control, or they're both in favor of gun control. So we want to take care to get independent sampling. So we might knock on the door and get a guy this time, ask him, and then go next door and knock on the door, and say the guy answered the door, and we say, well, let's speak to your wife, and tell them what we're up to, so it's not rude or anything, and then ask that lady, the wife of the next door neighbor. So the idea being that geographic distribution, or separating them out geographically, is kind of separating them out enough to think that we're going to get an independent way of thinking. Now that may not always work, because if the next door neighbor is a female to the next door neighbor male, and they talk in the backyard, you can see that there's a chance of corrupting the thing still. So you might want to take care in some kind of cluster sampling that we've talked before. Get some males in one neighborhood, some males in another neighborhood, some males in another neighborhood, and the same thing for females, to get some good geographic spread, with the idea that we're going to get good conceptual spread as well in terms of attitudes. Independent sampling is important. The other thing is that we pool N's. That's an N with an S. Excuse me. That our two samples, we pool them. So if this is 100, and this is 100, then we'll be working from a sample of 200. And this is an important concept because, let's just say that we had a sample of 32 males and 40 females. That would add up to 72, and that's less than 100, and that means we'd use the t-distribution just like we did in Chapter 8. So we pool these two samples in the math that you'll see here in a minute in order to get the total N in order to carry out our stuff. If this totals over 100, then we use the z-distribution. We're in a large sample size. If it totals less than 100, then we do the small sample size and use the t-distribution. Okay? Now, that's the concept of independent sampling and pooled. And for the most part, everything else is very similar. Although I have to say, the formulas, the concepts of the formulas are the same, but you'll find if you've looked at Chapter 9 that the formulas are more extensive, shall we say. There's more to them, maybe 2 or 3 stages to do each calculation. Whereas in Chapter 1 you might have just, or 7, one formula. Chapter 8 you might have a couple. But in Chapter 9 you can have as many as 3 formulas in order to get your answer. I just wanted to point out that for large samples where you're looking for a mean, you will look on page 210 of the text. You would do formula 9.41 first to get the numerator, and then you would do, and you can see, then you would plug that numerator into formula 9.2. So you have to do 2 formulas to get the large sample size with the mean. And he's got a really good application of that on page 212, and you can see, And there again you can see, as you would want to do in your homework, step 1, step 2, step 3, step 4, and step 5. Lay them out and make your whatever you got to do inside each area of each step. Do your steps and do your turtles. Now, one thing I want to point out again, like we did in Chapter 8, if you look on page 211 under the model of step 1, you're saying here they're independent random samples. Now, of course, if we were out there, you and me and all the rest of us in the class were doing this as colleagues and as a team, and we were constructing this thing, we would make sure, like we were just talking about a minute ago, that we were selecting men who we could have some assurance their thinking on gun control is independently of the women. In other words, we wouldn't be getting them from the same household and perhaps not even from the same neighborhood. Men from one neighborhood, women from another, maybe, something like that. Independent random samples. We would do that. And then when you get down to the third level there, that third line, sampling distribution is normal, we would have enough in each category, males and females, to assure we got that normal distribution. We know from Chapter 6, one of the theorems there, if you got something over 100, it's going to take a normal curve. And the larger the sample size, the more normal the curve looks. And you remember for the t-distribution, if it's less than 100, we assume normalcy, but it's flatter. You know, it's not as heaped up. It's got some good diagrams of that in Chapter 8, I think. Then that second line, level of measurement is interval ratio, I think is key to which formula you're going to go. You cannot do the, excuse me, you cannot do the formula for proportions for a mean, nor can you do the formula for the means for proportions, simply the wrong answer, straight. That's it. So be mindful. Level of measurement is interval ratio, so I've got to use this formula. Interval level of measurement is categorical, then I've got to use that formula. So just keep that in mind. One other line I want you to add, I'm not requiring you to, but I suggest you do, is add a fourth line that says sample size is less than 100 or sample size is greater than 100. If sample size is greater than 100, then you know you're going to use the z-distribution, whether it's categorical or a means, continuous. If the sample size is less than 100, then you're going to use the t-distribution. And that idea is the same for both Chapters 8 and 9. So just a little handy device, kind of keep you oriented. Stating the null hypothesis is just like we did in Chapter 8. Use the King's English. You can use a notation if you like, but I would say something in relation to this particular problem that he's talking about here, that the null hypothesis is basically, even though you can see on the bottom of 210, men score 6.2 on that scale and women are 6.5, I would say the null hypothesis says those numbers are basically they're numerically different, but only trivially so. It's a trivial difference and not statistically significant. And then you would, in your research hypothesis, you would say that those differences are statistically significantly different. And so put it in the English, it helps you keep it oriented. Then step 3 again is your sampling distribution. If it's less than 100, this would be a t-distribution. And here you can see that they're doing plus minus 1.96, which is a two-tail test. If the problem asks you to do two-tail, do two-tail. If the problem doesn't ask you, do one-tail. Because as a researcher, you would have done all your background work, you would have talked to people, you have done some focus groups with men and women, you would have been able to detect a difference, you would have been able to detect that women tend to be less in favor of gun control from your qualitative studies. You have done the literature review. Your own instincts might call you to make that determination. So there's no reason to go two-tail. You would know. You could set it either way. You could say, well, men are score significantly less, and so you go the left-hand negative side of the tail on a one-tail test. Or you could frame it the other way and say women are statistically significantly less likely, which would be they'd score higher on the scale, and then you'd put one-tail test on the right-hand side of your turtle. So anyway, where you got your alpha of 0.05. So you lay that out. Generally, again, unless it says two-tail, do a one-tail. And you can determine which tail by how you wanted to subtract the two values you see in front of you. All right, so computing the test statistic. There you see at the top of page 213, the first thing you see there is formula 9.4, that first several lines of formula. And then you see the z-obtained formula, which is formula 9.2. So you can annotate your text if you like. Just like you could at application 9.1, you can see the first formula is 9.4, and then you have the Z obtained 9.2. And we're looking at this one here, satisfaction with family life, with no children or at least one child. And you can see that it appears that people with no children have a higher satisfaction in life. Interesting study, no? And those with one child, at least one child, they're lower. And you can see how they go down through here, and they come with a Z obtained of 5.56, which if we were to, if we were to frame this out here, where we've got this, and this is our rejection zone, 1.96 and 1.96 on the negative side, and the score that he gets on this one is Z obtained is 5.56. It's way out here, 5.56, clearly larger than the critical value, so we would reject the null and say the difference between these two in terms of life satisfaction are statistically significant. That's the way the conclusion we would draw. You can see on page 213 the t-distribution. He doesn't have an application for it, but you can see on the middle of page 214, the N1 is 42 and N2 is 37. If we were to add that up, that's less than 100. So clearly we're going to use a t, when we pool it, we'll use a t-distribution here. And there you see the same sorts of things in the assumptions. You want to write those out. Write the assumptions out when you do step 1. Don't just blow it off and not do it. Do step 1 and write those assumptions just like you see them there and think them through. Sampling distribution is normal. Each one has a normal distribution. The males and the females, the one we did a moment ago. They're independent samples. The level of measurement is interval ratio. This one takes a different one, adds a different one about the population variances. We don't need to worry about that right now. That will take us back to chapter 4. But the variances are similar in the normal distribution. And there again you can see the null hypothesis and the research stated in the King's English. And then in step 3 you see the degrees of freedom. And there you can see that at 42 plus 37 minus 2, n plus n minus 2 is 77. So when we go to Appendix B, over here in the back of Healey, we find, go down the left-hand column of Appendix B and find 77. Well, when you do that, you'll go down and you'll find there is no 77 here. And the reason why those intervals begin to happen is because the larger the sample size is, the closer it gets to the Z distribution. So and you see it, you get down all the way to the bottom where it says infinity. Those values there are same as the Z distribution. But in any case, as you come down below 30, you can see 30 to 40. If you have let's go back and say we're looking for 77, so that it falls between 60 and 120 in that degrees of freedom column. But 77 is closer to 60 than it is to 120, numerically speaking, mathematically speaking. And it is he's got an alpha of 0.5. It's a one-tail test, you can see from step 3. So then we go up to the top tier at the top of the appendix where it has level of significance for one tail. We find 0.05, and we come down, and that's the third column over from the left until we come to about where 60 is, because we're going to use that. It's closer to 77 than is 120. And there you see 1.671. And we go over to Healey, and we see that's what he used, 1.671. And his finding, and his t obtained, is 2.16 on the negative side. So in that sense, the t observed is larger than the t critical. We reject the null, and then we say that the number of children in the central city and the number of children in the suburban city, or the family size, I should say, is statistically significantly different. It is a bit larger in the center city than it is in the suburban, or a little bit smaller in the suburban than the central. But we've statistically have found that to be the case. All right, and there on figure 9.1, the bottom 215, you can see how he lays that out with the turtle. Minus 2116 is far out, this way, in the tail here. And again, remember, these are probability distributions. The farther out you go, the more improbable that is to have happened by chance. So anything in here is similar. It could happen by chance. But out here, the farther out in these tails, remember this conversation we were having in chapter 8, the farther out it goes, the more improbable the occurrence is. So then the conclusions of you and me as statisticians is that it's so improbable it's not likely to have happened by chance, so we can reasonably comfortably reject the null in favor of our research hypothesis. And then we come over on page 216 where we've got it is a categorical variable here in the null, and we're trying to reject the null hypothesis. And here you see the 5-step model again, and you've got to do formula. You can see a series of formulas here. You'll do formula 9.7, then you do formula 9.8, skip 9.9, it's more of a formalized formula, formula 9.7, 9.8, and then formula 9.10 in order to solve this problem. And you can see in application 9.2, that's exactly what he did. You can see 9.7 is at the top cluster of formula calculations. The middle calculation set of calculations is 9.8, and the z-obtained calculations towards the bottom in step 4 is formula 9.10. So when you're doing your homework, follow these applications. He lays it out very well, and be sure again, step 1, step 2, step 3, step 4, step 5, and all 3 kinds of problems in chapter 9 and chapter 8. Do your steps and fill in the content. Okay. I think that's pretty much all that I want to say right now. And when you get over on page 220 and 9.5, I'll speak a little more about this in the review, but we have talked about it some. The size of the differences between these two is not really in our control, how different they are, males and females, say on gun control. That's not really in our control. All we can do is look at the difference and then test for the significance. The alpha level is in our control. Do we want to use an alpha level of 0.5 or an 0.1 or a 10? And generally we use an 0.5 unless the problem says otherwise. 0.5 is a nice compromise. If we do 10, our rejection zone is very big, and we might reject the null when we won't really want to when the null is incorrect. So we try and get out into the tail, and you get out there and you might fail to reject a null when you should reject it. So because it's way out there, you can't get a z observed or a t observed. It reaches that extent of the tail. So we compromise in the middle and do the 0.5 alpha, kind of splits the difference as a rule. So the alpha level is important. Generally you do 0.5 because you're not worried about if it's a high alpha rejecting a null you shouldn't reject, or if it's all the way out on the right hand side failing to reject a null that you should reject. Those are the type 1-2 errors that we've talked about before, and we'll talk about them again in the review. The use of 1 or 2-tailed tests, I think as a rule you would always want to use a 1-tailed test. There are some circumstances where you might not, but if you're in a competitive environment for funding, the last thing you want to do is go to the county judge for $250,000 and say, no, Judge, I don't know which way this is going to go. You will have done your research, you'll have done some qualitative studying, qualitative work in these communities, and you would have an idea, sense which way it's going to go, and maybe your own instincts, and you would call it that way with either a left-hand tail or a right tail. And then, of course, the size of the samples in your control. And we already know from Chapter 6, the larger the sample size you go with those theorem, the more precise, the more efficient the estimate is of the population parameter, or in this case the difference. You get a more precise estimate of the difference between the values in Chapter 8, which is kind of vertical, the parameter and your sampling finding, and over here between the two, it's more horizontal between the two categories, let's say, of men and women. So of course this is estimating what you would have found up here, but you don't know what's up here. You're just bringing down the sample and testing the significance between the two. You've got some idea up here, but you're it's more of a horizontal kind of testing significance. But again, the sample size, the larger the sample size, the more precise, the more efficient is your estimate of the difference. Okay, then they have a couple of other things at the end of the chapter that you can look at about how this works. So, I think that's it for now on Chapter 9. You have Chapter 8. Homework is due on Tuesday the 12th. I'll put a review together for chapters, I think we're chapters 6, 7, 8, and 9 for the exam coming up next week or so. I'm adjusting the syllabus because of things that have been going on here in a conference I went to. But I'll let you know tomorrow how we'll do that. And anyway, thanks a lot. and talk to you later.